So this was the problem that you tried to solve in the first quiz. The problem is you have three negative point charges which lie along a line as shown in the figure, and your task is to find the magnitude as well as direction of the electric field that this combination of charges produces at point P, which lies 6 centimeters from the 2 microcoulomb charge measured perpendicular to the line connecting the three charges. So I'm gonna call my uppermost charge as Q1, the middle one as Q2, and the last or the bottom one as Q3. Now, to facilitate the solving of this problem, I'm gonna illustrate this better using this one. So if you notice, um, over here, I have my Q1, Q2, Q3, the three charges, and these are the separation distances of each of the charges from the point P. Now take note, the problem asks that you need to solve for the magnitude of the electric field. Therefore, it's essential to understand that I will practically be measuring the electric field on a specific field point, in this case, the point P. And I have three charges here, so I have also three source charges. Okay, now basically, if you try to look into this one, you do realize that you need to solve something first. And the step one in solving for the electric field generated at the field point P, the red dot over here, is to identify and sketch the direction of the electric fields due to the three source charges. Now, if you notice, the three charges here are all negative. That means to say then that the electric field lines or the electric field vector from the field point P due to Q1 will look like this. So this is how it should be directed. It's toward the negative source charge. For the second source charge, as you might expect, since it is also negative charge, it should be towards that source charge, or Q2 in this case. And unexpectedly, or expectedly rather, you will notice that, or you should think that the third Q3, the third charge, should have an electric field pointing towards it since it is a negative charge. So you have now identified the three electric field vectors due to the three source charges from the field point P. Now the next step is to solve for the distance and angle between the charge Q1 or the source charge to the field point P. So you are going to find for, let's just clear this up. You're going to find for this blue distance, and by symmetry, if you will analyze the problem, the distance r is actually the same distance r from your Q3 to the field point P, because they're basically the same distance, 8 centimeters, 8 centimeters, and 6 centimeters. So by the symmetry of this problem, these should have the same length. So how do we solve for this distance r? I think it is apparent that we will be using the Pythagorean theorem in this case. So consider the case that your r will be your c, 8 centimeters will be the leg A, and 6 centimeters will be the leg B. So when we apply the Pythagorean theorem, we'll end up with this one. C squared, which is r, and then a squared, the two legs. This is your Pythagorean theorem, so I can rewrite this as c is equal to the square root of a squared plus b squared, where a squared, as I've said, is the 8 centimeters leg, and the b squared is the 6 centimeters squared leg, sorry. So after substituting the values, you get c is just 10 centimeters or 0.1 meters. It means to say that this distance r from my source charge Q1 up to the field point is just 0.1 meters. And so is Q3 to the field point, that is just 0.1 meters. And Q2 to the field point P is just 6 centimeters. Now after we are done with solving for the distances r, we need to solve for this angle theta over here. and so is this angle theta. But I'm hoping you do realize that because of the geometry of the problem, you have the same distance r, the same 8 centimeters, and the same 6 centimeters. They're practically the same triangle, so the angles for this one should be the same. But how do we get for this angle? So if you're going to recall your cosine function, cosine is ka from our mnemonic, right? So cosine means you take the adjacent over the hypotenuse. So if I'm going to take the cosine of this angle, my adjacent is 6 centimeters kasi yun yung tapad niya. And the hypotenuse is always opposite to the 90 degrees. And that's the longest leg of the triangle, right triangle. So that should be the 0.1 meters in this case, or 10 centimeters. So you try to simply substitute the values. Adjacent is 6 centimeters. The hypotenuse is 10 centimeters or 0.1 meters. Now I just used the centimeters in order for the units to cancel out. So I end up with this expression, and cosine theta is just 0.6. Now take note that I'm looking for the angle theta, so what I'm going to do is to apply the arc cosine or cosine inverse in the left side and right side of this equation. After taking the cosine inverse for the function cosine theta, I have this expression, and so I end up with theta is just equal to 53.13 degrees. So what that means to say in this problem, the angle between this one over here is just 53.13. Now, once we already solve for the distance and the angle, we're good to go to solve for the electric fields. So actually, the third step is to solve for the electric field vector of each of the source charges. But take note, at this step, we're only solving for the magnitude of these electric field vector, because we know this is a vector, E2 is a vector, E3 is a vector, thus it has components. Now at this point, we're simply solving for the magnitude of the electric fields. Now, let's take it per charge. So let's solve for the electric field E sub 1. That means it's the electric field due to the source charge Q1 on the top portion. And recall from our class that the electric field, or the magnitude of the electric field, is just equal to K and then the absolute value of Q over R squared. So when you substitute the values, you get this one. The K is just a constant with a value of 9 times 10 to the 9 Newton meter squared per coulomb squared. And then you multiply it by the absolute value of the charge, which in this case, the source charge is negative 5 times 10 to the negative 6 coulomb, or coulomb. And then you divide it by the separation distance. So this 0.1 meters should be the distance from the source charge and to the field point, because basically, again and again, the field point is the point where you're trying to measure the electric field. So after doing simple algebra, so you plug into your these values in your calculator, you end up with the magnitude of the electric field 1 to be 4.5 times 10 to the 6 Newton per coulomb. Now the next step would be to solve for the electric field due to E2. So in this case, the electric field E2 due to charge Q2. So we do the same procedure. Recall that it's just the magnitude of the electric field is just K absolute value of QR squared. And we're just going to substitute the values over here. So the source charge is 2 microcoulomb. So you have it here. The separation distance, actually, I mistyped this one. Sorry for this. The separation distance in this case is 6 centimeters, or that's 0.06. So kindly note that this is 0.06. And then when you calculate that one, you end up with 5 times 10 to the 6 newtons per coulomb. So this is the correct figure. However, I just mistyped this value over here. So next is to solve for the electric field, or the magnitude of the electric field due to charge 3. Okay, so basically we do the same thing. It's a boring thing. It's just K, Q over R squared. You plug in the values. So as expected, you should get the same value from E1, because You have the same source charge, if you notice, and the same separation distance from the source charge to the field point P. So without a doubt, you should get 4.5 times 10 to the 6 Newton per coulomb or newtons per coulomb. Now the fourth step, if you notice, is we're just able, from the third step, what we solve is simply the magnitude of these three vectors, but we do realize that each of the vector has components. So the next step would be to solve for the x and y components of each of these vectors. So let us start with the first vector, E1 or electric field 1. Notice that this portion over here is the x component of this first electric field vector. This one, the blue line, is your electric field along the y component. And this one is also the x component of the electric field 1. And the blue one is also the y component of the electric field 1. And again, recall that the angle is 53.13, this one over here. So if you recall, you're going to ask yourself, what is the relationship of this angle where the pointer is moving and my x component? And you notice that they are adjacent or tapat. So adjacent, so ka, it should be cosine. So recall that cosine theta is just adjacent over hypotenuse. And with respect to this 53.13 degrees, the adjacent side is your negative E1x. And the hypotenuse in that case is this E1 vector itself. So it's negative because it's moving towards the left x direction. So take note, in our class we say that after we identify the field point, we create another coordinate axis. So imagine you're creating another xy axis here, and you notice that your E1x is actually towards the negative end. So that is why you get negative E1x instead of simply E1x. Okay, I hope that is clear. So simply I'm looking for E1x, so I should get an expression of E1x is equal to, this should have a negative E1 cosine 53.13 degrees. So when you substitute the values, you get negative 4.5 times 10 to the 6 newtons per coulomb. This is just the magnitude of your electric field 1. And then you take the cosine of 53.13, which is approximately 0.6, and simply do your calculator thing, and you end up with E1 sub x, or the x component of the electric field 1, is negative 2.70 times 10 to the 6 newtons per coulomb. Now, we have just solved for the x component, so we still need the y component of this E1 vector or electric field due to charge 1. So to get that, we are sure, if you again look at this one, if this is my angle theta, I will ask myself, what is the relationship of this angle and the specific component that I'm concerned of? In this case, it's E1y. And obviously from the picture, it's opposite. The angle theta, this angle theta, and the component that I want are opposite with respect to each other. So the mnemonic would say so ka, opposite means so. So recall that sine theta is just opposite over hypotenuse. And from the geometry, you get that the sine of that angle, which is 53.13, is just the E1y, and it should be positive since it's moving up, over E1. The hypotenuse is still the E1 vector. So if you do a little bit of rearrangement, so you get E1y is equal to the magnitude E1 sine of 53.13. So this is a matter of calculator thing. So you plug in those values in your calculator, and you end up with the value of E1y to be 3.60 times 10 to the 6 newtons per coulomb. And recall, or note rather, that this has, or this should have, a positive sign, since your E1y vector, the blue one here, is actually on the positive y direction in your new coordinate axis. All right. So we have solved for the components of E1. So we are still to solve for the components of E2 and E3. But if you can recall from the geometry, or looking at this geometry, it's very apparent that for E2 this will be a very simple case, since the E2 vector lies specifically along the coordinate axis, particularly on the x. So that means to say we'll find out later that it should be along x. There should be no y component. All right, so this is your E2x and there is no E2y. But we're going to prove that mathematically. So if you're looking for this, the angle, the relationship of the angle, this is your angle 53.13 and E2x, again, they are adjacent. So from the mnemonic, it's the ka. Kasi yun yung nag-contain ng adjacent na component. So that means that the cosine of the angle, which in this case, sorry, it should not mention 53, but the angle, by the way, here in this case of E2 is 0 because that's the angle between the source charge Q2 and the field point. So the angle is 0 between them. So the cosine of 0 is just equal to negative E2x over E2. So rewriting that one or rearranging that, I end up with E2x is equal to negative of the magnitude E2 cosine of 0, and we know better that the cosine of 0 is just 1. So E2x will have the negative value, so negative 5.0 times 10 to the 6 Newton per Coulomb. Now for the y component, without solving, it's very apparent that there is no y component because, as I've said, the vector itself lies along the x-axis. But for the sake of mathematics, let's do the y component. So the y component, we take the sine. Sine theta is equal to opposite over hypotenuse. And maybe you just recall everything I said, that once you are sure that one component is cosine, automatically the other component will be sine. So in this case, we do this thing, substitute the values. But the very bottom line here is we know better that the sine of 0 will always be 0. So that is why we get the value that E2y will just be 0. All right, like this. Now we're done with the two vectors. Let's move to the third vector, which is the electric field 3. Now notice the blue part. This is your y component of the electric field vector 3. This red part is the x component of the electric vector 3. And so is this. This is also the x component, and the blue part is also the y component of the vector 3. Let's start with solving for the x component. So if I'm looking at my angle, this is my angle 53.13. And notice that I want this E3x. Now, just by looking, I realized that my angle and the E3x, which I want to solve, are adjacent. They are tapad. So I'm going to use cosine again, ka. So cosine of the adjacent side over the hypotenuse, adjacent is negative 3x because it's moving to the negative left side of the new coordinate axis, which you set the origin at the field point, and its hypotenuse is undoubtedly E3. So when we do a little bit of manipulation, we end up with E3x. This should have a negative sign over here, negative E3 cosine 53.13. So when you substitute the appropriate values, you end up with E3x. It's negative 2.70 times 10 to the 6 newtons per coulomb. And actually, you get the same measurement of x component with E1x because that's very obvious in the geometry of the problem. If it's not, you try to pause the video and try to look at the symmetry or the geometry of the problem, why E1x and E3x has the same x components. Now let's proceed to the y component, that is the blue part here. And when this is your angle, obviously that's opposite. E3y is opposite to the angle. So you get the so the opposite side, as I've said, is E3y. Then the other side is E3. The hypotenuse is E3. Now notice that there's a mistype here. So this should be negative E3y because the y component is along the negative side. So when you do rewrite this one, you end up with E3y is equal to, there should be negative E3 sine of 53.13. So when you substitute the values, I got it right here. I already have the negative incorporated. So when you do the calculation, you get negative 3.60 times 10 to the 6 newtons per coulomb. And if you're very observant of the values, the E3Y has the same value with your E1Y. It's just that it's the negative side. It has a negative side. And if you do really think about it, it's very apparent. This one blue here is your E1Y. This vector here, or I mean this component here, is your E3Y. So obviously they are equal in length, so they must have the same magnitude, but they are opposite. So that's why they are having a negative opposite sign. The one is positive, the other one is negative. So the fifth step is to add up all the components. So you solve for the summation of the x and y components of each of these vectors E1, E2, and E3, or electric field 1, 2, and 3. So along the x-axis, you take into account the sum of all the x. That means to say E1x, E2x, and E3x. These are simply the x components of the three electric field vectors. So you plug in those values that you have solved, and you end up with the sum of all the electric fields along the x component or x direction is just negative 10.4 times 10 to the 6 newtons per coulomb. Now along the y-axis, I'm hoping you're thinking that it should be 0. So you just take the same thing. You take the sum of all the EY. So that should be, there's a little bit of mistype here. There should be E1Y, E2Y, and E3Y. And substitute the values that you got from the calculation. You have 3.6 times 10 to the 6 and 0 for the E2Y, and negative 3.6 times 10 to the 6 for the E3Y. So apparently and obviously your EY is 0 in this case. So that means to say that at the field point P over here, the net electric field is towards the negative x direction only. Because if you notice, E sub EY is 0 and E3x has negative 10.4 times 10 to the 6. This means that if you happen to place, or if you place a positive test charge, say 1 coulomb, I know this is not realistic, but for brevity of discussion, let's say we put 1 coulomb charge over here, this will experience an electric force of magnitude 10.4 times 10 to the 6 Newton towards the negative x direction only. And there will be no pull along the y-axis. And this is telling you also that there is no electric force for this charge, for this test charge to be placed at point P along the y direction, because this is what you're getting. The sum of the electric field is just negative 10.4 times 10 to the 6 with no y component. And if you ask yourself, sir, why are we talking about the electric force when we have just solved for the electric field? So you just remember that your electric force is simply the electric field times the test charge, which is basically derived from the definition of electric field as the force per unit charge. Okay, so I'm hoping this clears up your solution for the quiz. And if you want the soft copy of this solution, I posted my LaTeX code in the Google class for your consumption.